Okay, so welcome to this next video in which we are discussing opioid receptors. Okay, so we're currently in the process of discussing the different families of G protein coupled receptors. Now, we've gone through 3 of the 5 families of G protein coupled receptors. We've gone through the rhodopsin family, which is the main family. We've gone through the secretin family, and we've gone through the glutamate family. We're now going to look at the adhesion family of G protein coupled receptors and also the frizzled/taste2 receptors. Okay, so next up is the adhesion family of G protein coupled receptors, and basically this family of G protein coupled receptors is special because the ligand for this for the receptors within this family of G protein coupled receptors is not your conventional idea of a ligand where it's some free molecule. Instead, it's components of the extracellular matrix. Okay, so if I draw the plasma membrane in here, then you have a large amino terminal domain here, which is going to interact with the extracellular matrix. And then you have the 7 membrane spanning alpha helices here, and then the carboxylic acid group inside. Okay, so here's the amino terminus. And basically this large amino terminal domain here will interact with components of the extracellular matrix. Okay, so I'll colour this in blue here. So this is some component of the extracellular matrix. Okay, so I'll put ECM, which is short for extracellular and then matrix. Okay, so all members of the adhesion family of G protein coupled receptors have large amino terminal domains so that they can interact with components of the extracellular matrix. Okay, and the final family of G protein coupled receptors is the frizzled/taste2 receptors. Okay, so frizzled/taste2 family of G protein coupled receptors. And basically, this family has the stupidest name, and the reason is that it's named after its 2 main members, basically, which are the frizzled receptor and the taste2 receptor. So again, it has a rather large amino terminal domain, and basically it binds its ligand on the amino terminal domain. Okay, but it doesn't have the special feature that the glutamate family G protein coupled receptors have, or the special feature that the secretin family G protein coupled receptors have. So in this case, it can't be categorized into any of these other ones. Okay, so you can't categorize it into the rhodopsin family of G protein coupled receptors because the ligand is bound by the amino terminal domain. You can't categorize it into this family because it isn't sort of lodged in between the amino terminal domain and the 7 transmembrane portion. You can't categorize it into this glutamate receptor family because it doesn't have the venous flytrap domain. Okay, so this is kind of what's left, basically. Those G protein coupled receptors which bind their ligand in the amino terminal domain but then don't have any other interesting features. Okay, so the 2 main members of this family are the frizzled receptor and the taste2 receptor. Now the ligand for the frizzled receptor is Wnt, okay, and the frizzled receptor then triggers the activation of the Wnt beta-catenin pathway, and the taste2 receptor, its ligand is bitter tasting molecules, basically, and it's involved in the gustatory system. Okay, so that's a brief whirlwind tour of the different families of G protein coupled receptors. Now, it's the rhodopsin family of G protein coupled receptors that we are interested in for opioid receptors. Okay, so all of the 4 opioid receptors are within the rhodopsin family of G protein coupled receptors, which means that they bind their ligand within the transmembrane domain portion. Okay, so basically there are 4 members. Okay, so 4 opioid receptors, ORs for short. Okay, so what now are the 4 different types of opioid receptor? Well, basically there is the mu opioid receptor, which I'll abbreviate to mu-OR. So this here, this is the Greek symbol mu. okay, and then it's the mu opioid receptor, so OR is short for opioid receptor, okay, so the O is opioid, and then the R is receptor, okay. Then you have the kappa opioid receptor, so kappa is another Greek letter, and then we'll have opioid receptor, so this is, it looks like a K, but it's a kappa, okay, so kappa is usually written smaller than K, basically. Then you also have the delta opioid receptor. So delta has this sort of curvy portion here. So this is delta. And then finally, there is one that doesn't really fit in with these ones, and this is the opioid receptor-like 1, okay? And for short, the opioid receptor-like 1 is abbreviated to ORL1, okay? So this stands for opioid, that's the O, receptor, that's the R, and then the L is for like, and then we have 1, so the opioid receptor-like 1, or ORL1, all 1. Right. Okay, so these are the 4 different opioid receptors. Now, they are all rhodopsin family G protein coupled receptors. So when the ligand binds to these receptors, they then change conformation, so I'll draw this. Okay, so here is the cell membrane. Then we have, within the cell membrane, are 7 membrane-spanning alpha helices, and then we have our carboxylic acid tail here, and all rhodopsin family G protein coupled receptors have very small amino terminal domains, so I'll draw the amino terminal domain here very small. Okay, and basically what will happen is the ligand will bind here, so let's show the ligand binding. Okay, so I'll show this as this little turquoise blob here. And basically, when the ligand binds, it will cause a conformational change in the G protein coupled receptor. And specifically, you'll get a conformational change in the 3 intracellular loops. And when those intracellular loops change in conformation, they will make available a binding site for a heterotrimeric G protein. Okay, so let's now talk about heterotrimeric G proteins. Okay, right. So, heterotrimeric G proteins consist of 3 subunits. Okay, we'll start with the arguably the main one, although as we'll see for opioid receptor activity, the other 2 are actually more important. Well, in some ways more important. Okay, so the main one is usually considered to be the alpha subunit. Okay, so I'll draw the alpha subunit here in red. Okay, and basically the alpha subunit has 2 states. It can be in the on state and it can be in the off state. Now in the on state, it has guanosine triphosphate, GTP molecules bound to it. And in the off state, it has guanosine diphosphate, GDP molecules bound to it. Okay, so let's say at the moment our alpha subunit is in the off state, so it has a GDP, guanosine diphosphate molecule bound to it. Okay, so this is a guanosine diphosphate molecule. Okay, now, the alpha subunit of heterotrimeric G proteins also has a lipid modification, basically. It has a lipid group attached onto it, which is what I've represented by this little line here. Okay, so basically, alpha subunits of heterotrimeric G proteins can have either myristic acid molecules stuck onto them, which is a 14-carbon fully saturated carboxylic acid. So it's what should officially be called tetradecanoic acid. Okay, so tetra for 4, decanoic to turn it into 14, and then fully saturated carboxylic acid. Okay, so myristic or tetradecanoic acid is a 14-carbon fully saturated carboxylic acid. There is also palmitic acid, which is a 16-carbon fully saturated carboxylic acid, and the real name for this is hexadecanoic acid. Okay, or the chemist's name for it is hexadecanoic acid. And basically, alpha subunits of heterotrimeric G proteins can have both myristic acid molecules and palmitic acid molecules stuck onto them. Some of them actually get both of them, okay? Most of them get at least one. Okay, so most of them have one, some of them have two. The point is that absolutely every single one of these alpha subunits gets at least one of these long chain carboxylic acid groups stuck off the side of it. Now, what's the significance of this? Well, basically, the long chain carboxylic acid group will anchor into the inner leaflet of the phospholipid bilayer. Okay, so this long chain carboxylic acid here will implant into this inner leaflet, and then that holds the entire alpha subunit just underneath the inner leaflet of the phospholipid bilayer, basically, and that's what holds the alpha subunit to the plasma membrane. Okay, so that's how the alpha subunit remains attached to the inner leaflet of the phospholipid bilayer. Okay, and then this is the alpha subunit. In heterotrimeric G proteins, you also have two other subunits. Now, the other two subunits always remain bound together. Okay, so the other two subunits of heterotrimeric G proteins are, you have a beta subunit and then also a gamma subunit. Okay, so let's show the beta subunit here in blue, and let's show the gamma subunit here in green. Okay, and basically the gamma subunit also has a lipid modification added onto it. Now, this is not quite as simple a molecule as myristic and palmitic acid. Okay, it instead gets a type of lipid modification called a prenyl group added onto it. Okay, now prenyl groups have a more complicated structure than myristic and palmitic acid. They are polymers or oligomers of isoprene. Okay, now if you know what that means, great. If you don't worry about it. If you want to find out more about it, I have an entire playlist on lipid modifications of proteins. I'm not going to explain it here because it takes me quite a while to explain prenylation of proteins. But the important thing to understand is that the gamma subunit has this lipid molecule, this very hydrophobic group sticking off the side of it, and this will implant into the inner leaflet of the phospholipid bilayer and hold the gamma subunit to the inner leaflet of the phospholipid bilayer. And basically the gamma subunit also brings the beta subunit, so it has the beta subunit with it. So overall, the beta and the gamma subunit, since they always remain together, people often refer to this as the beta-gamma complex, and overall the beta-gamma complex is going to remain at the inner leaflet of the phospholipid bilayer. Now, basically, when the alpha subunit is off and has GDP bound to it, it can associate with a beta-gamma complex, basically. So at the moment, they will be associated together, bound nicely together. When the alpha subunit has GTP bound to it, however, it doesn't associate with the beta-gamma complex, and instead both of them will be off and doing their own thing. Okay, so at present we have our heterotrimeric G protein here, and I'll just write that out. The reason it's called a heterotrimeric G protein is because each of these three subunits is different. That's the hetero. Trimeric means we've got three subunits, and then G protein refers to the fact that these are, well, the alpha subunit is certainly a G protein because it's got guanosine nucleosides bound to it. Oh, sorry, nucleotides rather. Guanosine nucleotides bound to it. Okay, right. What we now want to discuss is the range of different alpha, beta, and gamma subunits there are, and which heterotrimeric G proteins the mu opioid, well, all four of the opioid receptors work through. Okay, so we'll continue this discussion in the next video.